Welcome to the first Frontiers of Science lecture of the 2020-2021 academic year. My name is Peter Trapa. I'm Dean of the College of Science. As many of you may know, the Frontiers of Science lecture series is the longest continually running lecture series at the U. It was started by Pete Gibbs, who was then chair of the physics department over 50 years ago. And it really was a very innovative idea because at that time, there were few public forums to discuss science in the way that we're more used to today. In the intervening years, the lecture series has expanded in all kinds of interesting ways, but always the preeminence of the science has been central. And in fact, 23 of the lectures in the series have been given by Nobel Prize winners. This year, we're partnering with our friends in the Alumni Association to bring you this Frontiers lecture in this webinar format. And I'm joined by three of my colleagues in the College of Science in the chemistry department who will be leading the webinar. Let me briefly introduce each of them. Scott Anderson is Distinguished Professor of Chemistry. He's also the Henry Eyring Presidential Endowed Chair in Chemistry. He'll be joined by Shelley Minteer, who's Professor of Chemistry and currently the Associate Chair of the department. She's also the Dale and Susan Poulter Presidential Endowed Chair in Biological Chemistry. And finally, Henry White will be joining us, also Distinguished Professor of Chemistry and the Widtsoe Presidential Endowed Chair in Chemistry. Many of you will recognize Henry. He's my predecessor as Dean. He introduced many of these Frontiers lectures over the years, and I see that I'm still aspiring to the example he set for me. So without further ado, I'm going to turn things over to Shelley, who's going to begin with the slide presentation, followed by a brief video, and then I'm going to bring Shelley and Scott and Henry together for panel discussion, and then we'll wrap up with some Q&A from all of you, which you can bring your questions to the chat box and we'll curate them from there. So without further ado, Shelley.
Thank you, Peter. So I wanted to kind of introduce our center to you. So in 2017, we founded the Center for Synthetic Organic Electrochemistry, which is funded by the National Science Foundation. And we founded the center to make electrochemistry mainstream in the synthesis community to improve the safety and sustainability of producing chemicals, whether those be pharmaceuticals or agrochemicals or materials. And you may ask, why electrochemistry? And essentially, if you look at a lot of the synthesis of chemicals that is done at the industrial scale, it's done by using a lot of oxidizing agents and reducing agents. So you're using sort of a lot of chemicals that would be considered to have some safety issues associated with them. In electrochemistry, we're basically replacing those sort of chemicals that may have sort of explosive and toxic properties with an electrode and with electricity. So we're using electrons as our way to sort of produce those electrons or donate those electrons. And so we really see this as sort of a way that we can make a more sort of greener, more sustainable industrial process for making a wide variety of different fine chemicals and pharmaceutical chemicals. And so really our mission in this particular center is to essentially develop those new reactions, those electrochemical reactions to be able to make greener, safer, and more economic chemical production. And in order to do that, we don't just sort of make the reactions or develop new reactions and techniques, but we also have to train people. And so education is a great part of what we are doing, because we have to learn to educate the organic community on how to do electrochemistry. We have to educate our students in postdocs so that they can go out into academia and industry and government agencies and use electrochemistry. So we're kind of tying together both that innovation associated with new chemistry and new techniques with great education and outreach to the community so that we're teaching them how to use the techniques we're developing. So over the last 3 years, we've developed a pretty diverse team. And so if you look at this particular team, we basically have teamed together some people who have fundamental electrochemistry and analytical characterization techniques with the organic chemists who basically know the chemical reactions that need to be tackled and need to be approached, with computational scientists who actually can then help us to better design reactors and better design sort of predictive models for doing better chemistry. And so the team itself then has built a lot of collaborations with industry. So this includes collaborations with companies like ICA, where ICA is actually developing the equipment that we will use to do electrochemistry. So they're kind of on the equipment side of things, as well as collaborations with industries ranging from pharmaceutical industries like Pfizer to more agrochemical industries like ADM, to be able to sort of help them take problems that they have in terms of chemical synthesis and actually translate those to electrochemical systems and try to solve some of the problems that they have been having. So not only are we kind of building a consortia with industry in order to find out sort of what those pain points are that industry is having that we might be able to solve with electrochemistry, but we're also training academic chemists as well. So this is actually a map showing for the last 5 years all of the academic chemists from around the world who have actually came to the University of Utah Chemistry Department to learn techniques from us or to do experiments with us so that they could learn those techniques. So over the last 5 years, we've published 35 publications with those groups of people who have came to University of Utah to actually visit us and learn techniques. And we have many more, papers that are sort of in the queue, so to speak, where we've started the collaboration and it is either still ongoing or maybe has been delayed a bit because of COVID. So I think that number will be rising quite quickly. So really, if you think what we want to do, we want to have the innovation to develop new synthetic reactions, but we also want to train and mentor and educate the next generation of chemists. And so obviously a portion of that is teaching them science skills and teaching them the science techniques that they might learn in my lab or Henry's lab or Scott's lab, but it's also teaching them how to teach and teaching them some of those life skills. And so, we have partnered with the College of Sciences Science Research Initiative for undergraduates to actually do this. So we have a pilot program in the spring and the fall of the SRI program, where we had a cohort of students that ranged from freshmen to seniors who basically have been in the lab 9 to 12 hours a week, sort of learning our electrochemistry techniques. But at the same time, our graduate students and postdocs in Henry's lab and myself in my own lab have been learning how to teach those students electrochemistry techniques. So obviously it's a cycle where we need to teach them techniques, but we also need to teach them how to teach others. And finally, we have a strong collaboration with Nalini in our School of Biological Sciences and her STEM program to actually provide the center with training, not just on how to educate scientists, but also how to teach scientists to be able to communicate to the broader audience. So training them, we've had 8 training sessions so far, and the faculty and the graduate students and the postdocs have actually learned how they can communicate to the general audience about our synthetic organic electrochemistry. So if you look at it as a whole, the University of Utah has sort of brought together a series of other faculty from other universities, from Scripps, from San Diego State, from Caltech, from Cornell, from Brown, from Washington University, and from University of Minnesota and University of Michigan to try to tackle this problem of can we sort of make organic synthesis safer and greener using electrochemistry.
It's exciting science. It's a very important problem where there's just many opportunities to advance what we understand about making molecules. One of the big goals of this center is in terms of using electrochemistry to make complex organic molecules.
To essentially translate industrial synthesis to a greener, more environmentally friendly environment.
And so that will impact everybody.
We really want to bring synthetic electrosynthesis to the chemistry community as a whole. In order to do that, we have to develop new reactions, we have to develop new methodologies, we have to develop new instrumentation, and we have to change the way we educate the undergraduate student so it becomes part of their curriculum.
The genesis of the center was the idea that we could bring together a lot of people with different expertise to try to advance the field of electroorganic synthesis.
I'm an expert in bioelectrochemistry,
surface chemistry and electrocatalysis,
electroanalytical chemistry,
organic chemistry, organometallic chemistry, data science, and electrochemistry.
I think it's a blast. So putting a bunch of people together in very different areas is a lot of fun because you get to see how people build off of each other. And I think that allows us to be able to address bigger problems than you would be able to address if you're just a team of organic chemists or just a team of electrochemists.
Moving forward, science is becoming more and more collaborative as we develop skills from each other and interact. And that's really important in my future skill set.
Believe it or not, I'm not a chemist by training. I've gradually drifted from a mathematics undergrad through an interdisciplinary program.
When I moved here, I hadn't studied electrochemistry or even really thought about electrochemistry in research. I trained as an organic chemist. And really the center is designed to use electricity to do the reactions I was doing before, but in a different, more sustainable way.
And so I'm constantly learning, constantly challenged, but constantly being open to opportunities where my skill set can really build the program and I can add things to their work and they can show me problems that I didn't know existed, but actually I've got a skill set that can work towards solving. It keeps me on my toes and keeps things exciting.
And when I joined the center as an organic chemist, I needed to think about how to explain my science to electrochemists and vice versa. And then opening that up even further to talk to general population, the ability to interact in different ways, I think is very important for science.
Look at that! Look. The Center for Synthetic Organic Electrochemistry has partnered with STEMAP here at University of Utah, and they have provided us informal science communication training on how to speak to both the sort of scientific audience as well as the non-scientific audience. For instance, Ashley Cass, one of the graduate students in the program, is an avid skier, and she really wanted to bring electrochemistry to the ski slopes.
So one of the ways we started conversations on the ski lifts, doing our informal science communication, was to use these electrochromic goggles. They actually change color based on an applied voltage. You hit the button and it'll actually change to a darker lens. It kind of just jump-started our conversation about electrochemistry in general, which was a pretty cool thing to be able to do.
The CCI has a wealth of novel instrumentation. One is actually a scanning electrochemical cell microscope in a glove box to be able to do in situ imaging of electrosynthesis so that we can understand mechanism and further develop those techniques. So Scott Anderson has the unique capability of being able to make size-selected nanoclusters.
His ability to control matter at the single atom level and make new catalysts for carrying out electron transfer reactions. That's never been applied in the field of electroorganic synthesis. So this is really exciting.
I think the CCI has this great opportunity where we've spent the last 2.5 years basically building a team, building synergies, and starting that base of knowledge in terms of techniques and methodology that can go forward and grow entirely sort of new areas of electrosynthesis.
This centre is already making a difference in the world, and as it grows, that influence is only going to be bigger. From the academic scientists all the way through to industrial are getting on board already, and as the centre expands, well, the impact's going to expand too, so fun times.
All right. Well, that was a very exciting video. I hope you all enjoyed that. Now we're going to turn to the panel component of the webinar here. So I'm going to moderate a few questions for Shelley and Scott and Henry, who will join me for this panel and then we'll have a chance to get to your Q&A from the audience, so to speak. Enter your questions in the chat box and we'll get to that at the end. Okay, so let me start by asking Shelley a question here. You had that slide in your presentation about all the institutions, all the visitors who are coming to Utah, all these world-class institutions that you're engaging through the center on this project. But there must be challenges to bringing together so many researchers with different backgrounds, methodologies, perspectives, and yet you've been remarkably successful already. The center's already produced dozens of papers in this area. So, maybe you could speak to some of those challenges, how you embraced them, how you overcame them, what opportunities they presented, that sort of thing. So maybe you could say a few words about that, Shelley.
I think you're absolutely correct that anytime you bring in scientists, each of us in our sort of subdiscipline of science, we have our own language. So terms have been defined within, biology or chemistry or chemical engineering to have certain meanings that we understand within that subdiscipline. But when we start putting very diverse groups together, then language really becomes this huge challenge because to an organic chemist, the term substrate means the reactant that you're trying to react to produce a product. To Scott Anderson, a substrate is basically the surface that he's looking at, and to me as an electrochemist, the substrate is the electrode. And so that's one term that means something completely different to all three of us. And so, early on, we had a lot of video conferences where it was a lot of people asking, well, what do you really mean by that? What are you really trying to say there? And so coming together and finding a common language, and oftentimes our graduate students and postdocs are really helpful at helping us do that, is finding that common language so that we can all speak together and move forward.
Very interesting. Yeah, it sounds neat. Henry, let me ask you the following question. So you've done a lot of things over the course of your career, but the center is leading you in new directions. So how has this project diversified your own research portfolio?
Yeah, well, very much so. Let me start with that. So I'm sort of the old hardcore electrochemist in this group here. I've been doing electrochemistry for 40 years since I was an undergraduate. And my research, I'm sort of on the physical and analytical side in the past, really looking at questions like how far do electrons tunnel in solution to molecules? What's the structure of interfaces? So it's been more physics and physical chemistry. And now this group has me thinking about making molecules. So this is really out of my comfort zone. And it's really fun. We're doing just really expanding the types of things that we're doing in our lab. It's really challenging. I got to pick up an organic chemistry book and learn some basics so that I can actually interface with all these fantastic organic synthetic chemists that are part of this. So it's, but that's what's fun about research. I like moving around, and you learn something in one area and it turns out it's very important in a totally different area. And I think that's the whole idea about bringing all these people together, bringing different perspectives and different ideas together to really work on an important and challenging problem.
All right, well, let me throw the discussion over to Scott for a moment. So, before this project, had you ever considered applying your core expertise to making molecules? And what were some of the possibilities that occurred to you when Shelley approached you about this project and the possibility of the center?
So yeah, my background is in chemical physics, and specifically in surface chemistry and chemistry on particularly on the surface of nanoparticles. And I have never done any organic synthesis, and I've done very little electrochemistry. Henry and I had a few things we did a few years back with it. But it turns out that a lot of what we do is we look at chemistry on the surface of small nanoparticles that are on supports, and that's basically what a lot of electrocatalysts look like. And so we've been able to use our techniques to study, basically electrodes that are, functionalized with small nanoparticles that either we or other people in the center are using to try to do some synthetic work. So it's been very interesting. I mean, I have to admit that in a lot of these video conferences where the synthetic chemists are telling us about what they're doing, I haven't got a clue, because these molecules are way bigger and more complicated than I'm used to thinking about. But the fundamental stuff is very interesting. And so that's been an interesting new direction for my research.
Yeah, why don't you tell us a little bit more, go in a little bit more depth about your core expertise, that kind of surface chemistry.
So my background is in surface chemistry. So that's basically characterizing surfaces. A lot of things happen on surfaces in the world, including catalysis. And so we've developed techniques for characterizing surfaces, but also for preparing surfaces. And so we've used these in a couple of different ways, this expertise in a couple of different ways in the center. For example, on the applied side, my group has quite a bit of expertise in characterizing nanostructured surfaces. And so, we've had opportunities to collaborate with people like Phil Barron at Scripps, who's a synthetic chemist, and with people like Shelley and Henry, who are, really electrochemistry experts, to unravel some really complicated electrochemistry that the synthetic chemists are discovering. And so, for example, what we've done in that is try to characterize the electrodes and try to look for correlations between electron structure and what's going on in the electrosynthesis, try to understand how the electrode nanostructure is affecting the reactions. On the more fundamental side, my group has developed a unique capability. I think we're the only group in the world that can do this, that can prepare electrodes that are covered with catalytic metal clusters, which are basically small nanoparticles. But what's unique about this is we can control the exact size of the particles in the size range between about 1 and 30 atoms. So we can pick out, platinum 10 and put down a layer of all platinum 10 clusters. And then we can just adjust, we can tune that however we like it. And so this gives us a new way to probe reaction mechanisms, because basically we can look at how the particle size affects activity, catalytic activity, but we can also look at how that, we have all kinds of tools for characterizing the electronic structure and the morphology and other properties of these small clusters. And so we can get information about, what physical properties are controlling the chemical activity. And so we're applying this to CSOE, to the center, to examine things like how the cluster size affects activity for reactions like glycerol oxidation, which is it's a relatively simple reaction by CSOE standards. But it's an important reaction for converting glycerol, which is a byproduct of like biodiesel production, into something more useful. And so, we've kind of applying these very fundamental techniques to looking at somewhat more complicated problems than we would normally.
Yeah, it's remarkable, the level of precision that you mentioned. But which you talked about at the end is maybe a nice segue into this next question. That Shelley led off with talking about industrial production of pharmaceuticals. It involves a lot of nasty oxidation reduction reagents, and that this project may hold a great deal of promise for greener ways, more sustainable ways of making molecules, making pharmaceuticals potentially. So could you talk about that a little bit, Shelley? I found that really interesting when you led off with that.
Yes. So if you if you think about electrochemistry, your need is really electricity. And so you can get sort of green renewable electricity from solar or wind, and then use that directly, as opposed to actually having to produce these sort of reducing agents or oxidizing agents. And usually in the production of those reducing agents or oxidizing agents, you will produce greenhouse gases. So you can kind of minimize your greenhouse gas production, as well as sort of your chemical waste. So obviously, if you're using electrons, we don't sort of have to think about chemical waste associated with electricity. But if we're adding oxidizing agents or reducing agents, then we're going to have to think about the waste product associated with all of those.
Yeah, it's fascinating. And I want to also kind of return to what Scott was talking about a little bit. I mean, how has collaborating with new disciplines, with Scott, surface chemistry, or we haven't really touched on another important member of your team, Matt Sigmund, who's chair of the department now, and he's increasingly moving into data science applications to synthetic chemistry and organic chemistry. So how have those connections influenced your own work? And maybe you could even, if you have any surprises, were there any surprises that you encountered? I'm sure there were several, but if you maybe could talk to something that really was unexpected.
Yeah, so my background is basically looking at nature as essentially a source of inspiration when it comes to thinking about electrochemistry. So for the most part, my background has actually been in sort of mimicking natural processes for energy applications, so not for synthesis applications at all. And about, I don't know, 7 years ago, I actually was kind of challenged in that we had a system where nature could do a chemistry that we actually couldn't do on an electrode surface. And so I actually went to Matt Sigmund, so one of my colleagues and now the department chair, and invited him to lunch. And I was like, I'm really struggling with this. I'm really struggling with sort of the fact that we can't get nature to do exactly. We can't get nature on an electrode to do exactly what we want it to do. And he basically came back with some examples in organic catalysis, where we might be able to make hybrid systems that were partly using that biological inspiration and partly using organic catalysis to sort of address this energy issue, this energy application that we had. And so we started a collaboration. We started using some of his data science tools for these hybrid systems. And as we went along, he kept saying, we're using this for energy, but it can be used for other applications as well. And he kept talking about organic synthesis. And at some point, I walked into Ryan Looper, one of the other organic chemists, faculty members in our department. And I'm like, you don't have a potentiostat, which is the instrument that an electrochemist uses. You don't have a potentiostat in your lab. What would it take for you to buy a potentiostat? And he basically named a series of reactions, one of those being the Birch reduction, that because of safety reasons for his students, he would buy a potentiostat to be able to make his lab safer. So it became a sort of safety issue. And I never really thought about it from that perspective before. And so we really started then, looking at what are those sort of processes. And the Birch reduction, used to be in an organic chemistry lab 50 years ago. We would actually teach students to do this, and now for safety reasons, we don't do that. And so he brought that up. We later met with Pfizer. They also brought up these sort of reactions that for safety reasons they couldn't scale up. And so, Scott's group and my group, Phil Barron and Matt Nurok, who's a computational chemist, then kind of came together as a group to see if we couldn't find ways to do those electrochemically and sort of address that safety issue. So I didn't think that I was sort of getting into electrosynthesis from the sort of safety issue. I was thinking as an energy person, I was getting into it from more the sustainability issue. Definitely that has transitioned with time.
Interesting. I want to kind of continue in the surprise direction and ask Henry. I mean, one of the most exciting things about doing science or doing mathematics is formulating new questions and new questions that you could never have imagined even having the language to formulate just a few years ago. So are there any new questions in your work, Henry, that you're asking today that this project has inspired that you're excited about?
And I need to unmute before I talk. Apologies. Yeah. This is really exciting project. It's really, just working with all these other collaborators. I think we have joint group meeting every week with 20 groups at 8 or 9 universities, and you listen to these people and you can just imagine all the things you can do to contribute to moving this project forward as a group. But the ideas really come from listening to other people. I'm sort of psyched up on two areas. One is that we do, besides experimental work, we do a lot of computational work in the past looking at transport and kinetics. And now these organic reactions are much more complicated than anything that my groups looked at in the past. And when we start applying this, it becomes clear that I can't do this on my own. My students can't do this on my own. I have to talk to Shelley, Matt, and figure out the nuances of the chemistry, what bonds are likely to be made, et cetera, et cetera. So that's been a lot of fun. And then something else we're doing, and this is kind of with Scott. Scott talked about his ability to deposit single atoms and small metal clusters. And we're doing some work like that too, where we're actually making an electrode that just has one atom that's active on the surface. And we know from our previous work, we can measure currents at such a device, and this would have been just unthinkable 5 years ago. And now the idea is can we use that to start looking at some of these organic reactions and to see what happens when you get down, when you're able to control structure at that level. So it's all exciting, and I think there'll be a lot of new things going forward as well.
Yeah, I mean, that's another example. It just blows me away, that level of precision that you're able, kind of the atom level that you were describing and Scott was describing earlier, these tiny clusters. Very exciting. I want to turn to a few questions about education and outreach. That was in the video, and Shelley mentioned training of students in her slide presentation too. So maybe I'll ask Shelley this one. We're in the middle of a global pandemic. How do you keep your trainees engaged? You've thought about this a lot of different ways. In your role as associate chair, you've really taken a leadership role along with Matt in safely and effectively implementing undergraduate lab courses on campus. And it's a big part of how you train your graduate students now under the circumstance of the pandemic. So maybe you could talk a little bit about that, and what are some of the safety protocols that you're putting in place? You touched on safety in a different context in the last question that I asked you, but maybe you could talk a little bit about what you're doing to keep your students, your group members safe these days.
Yeah, so I think the start of that question is how to keep them engaged. You want to keep them engaged as much as possible, and obviously Zoom has become sort of our standard way of staying engaged with students and postdocs, from the good of that and the bad of that. And obviously, normally I would walk through the lab every afternoon and talk to everybody and sort of make sure that that things were going forward. We can't do that in person anymore. So instead, that's, having a series of Zoom meetings. And I think, all of us within the center are very aware of that. So our weekly meetings, where you basically have 15, different PIs, are really, a lot of, inspiring the students. Hey, I know that this may not be going as fast as you want it to go, because of COVID restrictions, but you're making progress, and we're very excited about that. So, but definitely, you know, inspiring them becomes important. If we look at, you know, what has happened since March, so we basically spent as a department about 8 weeks where we were all sort of teleworking, and I think that's probably the biggest challenge to the students, because they get worried about their careers, about their education, and is this going to is this going to affect, you know, their education and their long-term career goals? And at the time I was saying, oh, this is just going to be a short time, and I think it's going to be a bit longer time. But at that point, you know, the department really spent a lot of time sort of thinking about how we could safely get back into the research labs. And in chemistry, we had this sort of advantage in the chemistry labs, and the chemistry building was basically built to handle the fact that we work with toxic chemicals. Not usually toxic biologicals like COVID, but toxic chemicals. And that means that we have a lot of fume hoods that are bringing in, taking out sort of contaminated air and bringing in fresh air. So we have a lot of air turnover. And so that helps us in terms of, you know, thinking about how we can safely go back into the lab. And so, you know, are we back into the lab? Yes. We are back into the lab with lower people density so that, you know, everyone can social distance. Everyone has a mask on. We're not eating and drinking in the building. So we're doing sort of everything that we can to make the students who are there as safe as possible. And part of that, I think, affects the community that they feel, because typically labs are our communities, and they spend a lot of time sort of chatting with each other, or you know, in the offices having coffee or having lunch, and we're kind of removing that. And so we're replacing that with a lot of sort of virtual Zooms and a lot of interactions from that perspective. But we kind of have to do that to ensure that we can keep them safe.
Yeah, I'm really grateful to what the chemistry department has done in the safety direction. I was reviewing some data earlier today with the liaison to the contact tracing team with the College of Science liaison, and I was very proud to see that there's been zero evidence of virus transmission in College of Science buildings, in chemistry buildings, despite all the laboratory research which is continuing on in those spaces. And that really is testament to the kinds of things that you were describing. I want to ask Scott this next question, and you know, we've been reflecting a lot about the collaborative and inclusive nature of the center, and how does that affect your approach to mentoring, you know, inexperienced students, inexperienced postdocs, or maybe even colleagues who have very little experience in surface chemistry? And then how does your experience as an educator, your approach to mentoring, influence your own research? Maybe you could talk a little bit about that too.
Yeah, I mean, other people have already mentioned this, that you know, one of the nice things about a center like this is that there are lots of researchers with different expertise, and we have these, you know, that's basically giant group meetings every week. And so this gives a chance for, you know, students to interact with each other, you know, students and postdocs, but also with the PIs in the center. And so there's a lot of mentoring going on. Some of it's deliberate and some of it just happens. And that's, I think it's especially important with COVID, because we don't, you know, you can't just walk down the end of the hall and, you know, talk to Henry or Shelley anymore. So that's, but they, you know, the students actually are sort of still doing some of that, I guess, because they're allowed to work in the building. So I think that's, you know, a very important thing. And you know, what we learned from these weekly sort of group meetings with the rest of the, you know, video group meetings is, you know, we learn new science, and we also, you know, often see problems that other people are having where you can say, well, okay, this is something that we could, you know, it gives us, you know, both research ideas, but also ideas for, okay, we could, you know, this would be really easy to help these guys out, you know, get them to send us some samples to look at, or we will, you know, whatever, do some experiments to try to help them. From the, you know, I mean, for me, the reason I like being a teacher is because I like learning things. And, you know, university environment gives me the opportunity to keep learning things all the time. And, that keeps things fresh. And it, I feel like, it's a collaborative project between me and my students to learn stuff. And so the center gives, because there's lots of new, I tend to pick, if I were left to myself, I would pick research problems that I would really drill down in, very fundamental problems that I would really get down into the nitty gritty with. And, typically would avoid the kinds of really complicated, messy problems that are involved in organic electrosynthesis. But, being part of the center helps us ease us into that, and there are experts there who can, deal with the complicated, messy bits, but then we can use some of our expertise to try to help them out. And, in the process, we learn a lot about how to deal with these more complicated problems. So it's a very interesting process, I think.
Yeah, and that is the exciting thing about being a professor, a teacher, a researcher, that the potential for the infinite opportunities to continue learning new things. Very exciting. Henry, let me ask you about a slide. It appeared on slide in Shelley's presentation about the Science Research Initiative. This is a program designed to introduce more undergraduate students to research early in their careers. And I know that you and Shelley have taken on a number of students in your group under the umbrella of the Science Research Initiative. And of course, I don't have to tell you any of this preface because this is your brainchild. One of the last in your last year as dean, you launched this idea, and I've just been trying to not mess it up so far and keep the momentum going. Why don't you say a little bit about the Science Research Initiative and how it interfaces with some of the activities in the center?
Yeah, sure. Well, I think you described it pretty well there. I think the idea is to get a very large number of students when they come in the door as freshmen involved in science and research in all the various departments. And I suspect the pandemic has kind of put the brakes on this a little bit because it's hard to get these students in the lab. And this started about a year ago, approximately. But Shelley and I, once that program, the SRI program, got approved, and the CSOE, this NSF program that we're involved in, once it looked like it was starting to take off, we jumped on this as one of the pilot SRI groups. And so we have 6 or 7 students. I've forgotten the number. I don't actually get to see them because of the pandemic, but they are very involved in the SRI program. Shelley's got a fantastic postdoc who's working with them. I have a graduate student who's working with them, and they're being trained in all aspects of the center project. So they're getting formal training by Zoom, for instance, on the fundamentals of electrochemistry, electrochemical methods. And they're also learning all the techniques that one needs to know for organic synthesis. And then on Saturdays, they're actually in the lab on Saturdays this fall doing experiments. And they're participating really in the research. Tomorrow, we've got 6 of these students, and they range from sophomores to seniors, and some of them are biologists, some are chemistry students. There's a physics student. We had an engineering student who was part of this. But tomorrow they're all going to give 10 or 15-minute presentations at Shelley and our joint group meeting. And some of these students have really been participating very actively on their own. And there's 3 or 4, I think, they're going to be co-authors on a paper that's been drafted and is getting ready to be sent out in the near future. So all these students, they're getting exposed to organic electrochemistry, but more importantly, they're being exposed to scientific research and methods one uses in research. Some of them may go on to graduate school in chemistry and pursue this type of research, but some of them will go to med school, and some will go out in industry and do great things. So the SRI, the big program, is really I think it's got a lot of potential to impact a huge number of students and get more of our undergraduates involved in research.
Yeah, and if you think about a lot of, I mean, the timeliness of the SRI program, I mean, we read a lot of gloom and doom predictions about the future of higher education, but what Henry just described there is something that there's no way to recreate that in-lab experience online or even reasonably approximate it. And so this is a way that those experiential learning opportunities come together with the research, world-class researchers like Henry and this team that we have here today. And that will just be a big part of the future of the college, no matter what happens in the online space. All right, so we're getting kind of, we need to wrap up the panel discussion here before we turn to a little Q&A. I thought I'd give maybe Shelley the last word here to just think really broadly. In 10 years, what do you see as the impact of the center? That's a pretty big question, but maybe you could say a few words about that.
Yeah, so I think, there's a number of impacts of the center, and obviously, we're doing basic research to fundamentally understand these reactions better. And so, that's our goal from the research side of things, and what we, sort of hope to see as we go forward in the next 5 to 10 years. But really, I would say, the product of the center is going to be the people that we train and we educate. And the ways that we change chemistry education going forward. So putting electrochemistry into, the organic chemistry curriculum as an example of that. So really this sort of interdisciplinary training where a student in my lab is getting training in Matt's lab and Scott's lab, and is kind of getting, learning that sort of those language issues and learning a new language to be able to communicate in this sort of interdisciplinary and multidisciplinary way. So I think that will be sort of our 5-year goal, so to speak.
Yeah, and if you think about the power of what you just described, the training the next generation, part of what makes all that possible is our country's investment in basic research, NSF's investment in the center, marrying the expertise that we've assembled here at the U with that basic federal funding really is an investment for all of our future, our collective future. Okay, so let me just throw a couple questions to all three of you, and you can choose who would best address it. But let me start with this one. So what is an example of reaction? So maybe you could, doesn't have to be too detailed of an example, but tell us an example of a reaction that can, in some sense, be done better with electrochemical methods when compared to conventional mix, heat, stir, what we think of very basic methods in synthetic chemistry. What's something that is actually done, an example of something that's done better with electrochemical methods?
So I guess I have a couple of examples. Part of it is what you define as better, right? So I talked about the birch reduction. The birch reduction is definitely a situation where industry really can't do a birch reduction because of safety. They can't scale it up because of safety issues. And we've been able to translate that to something that can be done on the desktop, so to speak, or the lab bench, but also that Pfizer has been able to scale up and sort of maintain safety while scaling up. So that's an example of where better is safer. But the other thing that really advantage electrochemistry has is that electrochemistry can drive things far from equilibrium. And so my group works in a lot of systems where we're essentially using electrochemistry to shift something that, if you use the standard mix, heat, stir method, is a reaction that is basically shifted towards reactants instead of shifted towards products. So its equilibrium is not ideal to be able to produce products. And we use electrochemistry as that driver to drive things far from equilibrium.
Makes sense. Any Scott or Henry want to chime in before I get to the next question? I'm happy to just go to the next one. Chance, okay. Scott.
Well, I mean, there are, Shelley pointed this out already, in that a lot of the reactants that are used to do reductions or oxidations are pretty very reactive molecules. That's, they need to be in order to do it. And so there's hazards associated with them. There's also a lot of waste, chemical waste that has to be disposed of. Whereas, in an electrochemical setup, basically you're just pumping electrons in, and assuming you generate the electrons in some green way, then, you basically don't have any waste. You still have some chemical waste of solvents and whatever that you're using in your reaction, but you don't have these nasty, reactants that you're working with, and all the waste they generate and all the waste that was generated in making them in the first place. So it's, a more, safer, but also more sustainable.
Let me add one comment to all of this, and it might have been said earlier by Shelley. The key idea is the electron is a reagent in electrochemical synthesis, and so we're using electrons instead of using, for example, strongly reducing agents like sodium metal. We can carry out reactions, and we don't have to worry about the sodium metal, which is a safety hazard. You don't have to worry about disposing of stuff. And for all practical purposes, electrons are free, because it's the same thing as, if you have a 75-watt light bulb lighting up your desk, that's the type of electricity. We actually use a lot less to carry out these reactions. And so it's really, it has potential for being an incredibly inexpensive and safe technology. And as Shelley, I think, started off explaining at the very beginning, part of this is really getting the chemistry community to adopt some of these ideas. They're a little fearful of using electricity just because they're not trained in using it in their chemical synthesis. But there's the environmental and the safety issues there's just huge potential to have an impact here.
Yeah, you mentioned sodium metal. I'll relate a little anecdote from my undergraduate days where we got a hold of a chunk of sodium metal and threw it in Lake Michigan. So it wasn't a particularly safe experiment, but so you're doing things much better. But on a more serious note, which you're all talking about, and there was that slide with all these potential industrial partners. I mean, this could really revolutionize big parts of how companies make their chemical products from the perspective of being more safer and environmental friendly. So a huge potential there. I think everyone recognizes that. So very exciting. Okay, so we're getting kind of near the end here, and I think I'm just going to wrap up with one last question. So suppose a student is in the audience here today, out there watching our data packets in one form or another. How could they get involved in the center, in this kind of project, in this kind of research, learn more about it, get connected with some of the activity that's going on in the center?
All right, so I think Shelley and I clicked on it. Well, Shelley, we probably have slightly different answers, but you're talking about undergraduates, right, Peter?
Yeah, I'm talking about that. I was thinking about
students already have a good pathway to get involved in this.
Yeah,
I think the undergraduates, through your office, signing up for the SIR program, that's one way, but directly contacting Shelley, and Shelley's got a team of staff that can get people involved. And these students can contact Scott or Shelley or myself. And I think we'd love to have more people involved. We'd really like to see the SRI grow. And we're hoping, we've got 6 or 7 undergraduates, but we're kind of shooting for 20 in the future, steady state. So I think we'd all be very receptive to hearing from undergraduates. Just by email is probably the best way.
Yeah.
Well, that's great. I mean, that you're so open to just talking to students directly via email. And as you mentioned, Henry, in the dean's office, we've got this SRI program, which includes not only research projects in this space that we've been talking about, but other ones. And so that's another place where students should look to if they're interested in getting involved in all kinds of different research projects in the College of Science. Well, I think that's a great spot to stop. I want to extend my sincere thanks to my friends and colleagues in chemistry, Shelley and Scott and Henry. It's always a pleasure talking to you. I'm so humbled and excited really by hearing all the great things that you're doing, and look forward to, maybe another frontiers in the next couple of years, reporting on all the great things that have come out of the center during that time. So until then, take care.